According to Azwa and Yahya 2023, ground subsidence refers to the sinking or downward movement of the ground caused by weakened soil structure, erosion, excessive groundwater, or unstable slopes. This problem often occurs in hilly areas where human activities such as construction and poor drainage disturb the natural stability of the land. Ground subsidence can lead to landslides, structural damage, and even building collapse. One of the most well-known cases in Malaysia is the Highland Towers collapse, which happened on 11 December 1993 in Kuala Lumpur. Block 1 of the 12-story condominium collapsed after a major landslide, causing 48 deaths. Investigations show that the disaster was mainly caused by prolonged and heavy rainfall, poor drainage systems, and failure of the retaining wall behind the building. Water from a nearby diverted stream leaked into the soil, increasing groundwater pressure and weakening the foundation of the tower. Three major issues contributed to the collapse. First, groundwater accumulation, which excess water saturated the soil and weakened the ground beneath the building. Second, poor drainage system, where broken diversion pipes and uncontrolled water flow increased soil erosion and instability. And the last one is retaining wall failure, which is the retaining wall behind Block 1 collapsed due to landslides and pressure from waterlogged soil. The Highland Towers tragedy highlights the importance of proper geotechnical design, slope monitoring, and effective drainage system in hillside developments to prevent future ground subsidence disaster.
48 people died on 11th December 1993. This was not just a natural disaster, it was a failure in engineering professionalism, ethics, and law. Here is what went wrong. From the Code of Professional Conduct by BEM, every engineer has one main job, which is to put the public safety first. At the Highland Tower, project engineer Wong Yuan Kim has three clear responsibilities. Number 1, design a drainage that can cater to heavy rain. Number 2, supervise the construction and ensure the drainage is actually built. Number 3, only certify a building as safe after confirming that everything is working properly. He failed all three. The Board of Engineers found him guilty and struck his name off. He can never practice as an engineer ever again. BM found two major ethical failures. Charge number 1, Wong signed the certificate of fitness allowing residents to move in. The drainage system was not completed. He knew and still let people live there. Charge number 2, Wong ignored the steep slope directly behind the Block 1. He didn't check whether it was stable and he didn't design any retaining wall or foundation to handle a landslide. A visible and obvious risk completely ignored. These were not honest mistakes, they were choices. He chose to finish the project fast instead of finishing it safe. This ethical failure didn't happen by accident. The system was weak and the law were not enforced properly. Act 133, the Street Drainage and Building Act, allows fine up to RM500,000 or 10 years in jail. But Selangor already replaced the mandatory government inspection with a self-declaration systems. Engineers could simply sign off their own work. No one checks. That system is still used today. The UBBL 1984 Section 258 says the person who submit the plan is responsible, even if the local council approves it. That is why developers, engineers, and architects were all found liable in the court. And the Land Conservation Act 1960 bans development on steeper slope than 18 degrees. Highland Tower was built on exactly that kind of slope, in one of the rainiest areas in the country. How was this ever happen? The laws existed, but they were not enforced, and 48 people paid the price. So, who was involved? The engineer and the developer wanted to finish the project fast and save money, while the neighboring landowners neglected their drainage and was found 30% liable. The local council approved the project and gave the certificate, but was protected by the law. And the residents, they just wanted a safe home. They trusted the engineers. They trusted the system. Unfortunately, 48 of them died. The lesson is simple. When engineers cut corners, people die. As future engineers, this is a failure that we can never repeat.
First solution is slope stabilization technique. Slope stabilization technique, like retaining wall, provide immediate mechanical support to slope by resisting lateral earth pressure. Main component of retaining wall include such as wall system, base or foundation footing, backfill material, and drainage system to prevent soil movement and progressive failure. In addition, retaining wall contribute to SDG12 by preventing slope failure and reducing the need for repeated reconstruction. Next sustainable solution is green infrastructure integration. This solution uses infrastructure trench, vegetated swale, and wetland vegetation to reduce runoff and infrastructure pressure. Furthermore, green infrastructure support groundwater recharge and enhancing soil protection through vegetated system, making it consistent with SDG 12 principle of responsible resource management and sustainable infrastructure development. The third solution is smart monitoring and preventive maintenance system. This solution uses IoT Internet of Things based sensor to detect early sign of slope movement, subsidence, and landslide risk in real time. This system improves safety by providing early warning that contain resolution, coverage, usability, and frequency that enabling preventive maintenance before major failure occur. The approach is sustainable because support long-term infrastructure resilience. The solution is utilizing permeable pavement. Permeable pavement contributes to subsidence and slope failure mitigation by reducing surface runoff, controlling infiltration rates, and minimizing soil erosion. The pavable pavement contains surface layer that allows rainwater to pass through surface opening, base layer, bedding layer, and sub-base layer that function as temporary water storage before infiltration. In hillside developments, the system can reduce excessive storm water concentration and improve drainage efficiency. Also, this method can connect with SDG 12, where it can reduce maintenance and repair waste.
Moving on into the societal implication of our case study, we must recognize that engineering is not just about structural stability. It is about protecting the people who inhabit these spaces. For the Highland Tower project, our focus centers on three pillars, which are public safety, community resilience, and also stakeholders' transparency. We are advocating for a solution that prioritizes human life and also social responsibility. The primary societal benefit of implementing smart monitoring and robust stabilization is the prevention of catastrophic loss of life. The 1992 Highland Towers collapse resulted in 48 fatalities, a tragedy that served as a common reminder of the consequences of engineering failure. By shifting towards sustainable, monitored solutions, we fulfill our ethical duty to ensure that no community has to face such a loss again. Our goal is to transform the site from a symbol of tragedy into a model of safety. To achieve this, we utilize IoT technology. By installing tilt and pole pressure sensors, we create a reliable alert system. This is crucial because hillside risks are often unfamiliar or infrequently encountered by the general public. This sensor provides authorities and residents with the critical golden time needed for a safety evacuation. This technical solution directly translates to providing peace of mind and a concrete safety net for the community. One of the major causal factors identified in past Malaysian landslide is the lack of coordination and communication between agencies. Our purpose smart monitoring system address this by enabling real-time data sharing. By making this data accessible to both technical department and the public, we ensure transparency. This prevents information silos and ensure that everyone, from the engineer to the residents, is aware of the site's condition, thereby fostering a culture of accountability and shared responsibility. Finally, we must consider the psychological impact of the built environment. While traditional concrete structures look industrial and imposing, our purpose green infrastructure such as vegetated swales and bioretention areas improves the aesthetic value of the neighborhood. Beyond this beauty, this natural element has a positive impact on the psychological well-being of residents. Creating a landscape that works in harmony with nature creates a more livable, resilient and inviting community space.
So as for this section, I will evaluate the environment implication and consequences of the proposed sustainable engineering solutions. This includes slope stabilization techniques, green infrastructures integration, smart monitoring, and preventative maintenance, and the use of permeable pavement. So this evaluation is supported by reliable secondary resources including JKR Churun 1, the National Slope Master Plan, the Syria Search Manual, and public research on permeable pavement and stormwater management. So firstly, the proposed solution can help protect soil structure and slope integrity. From an environmental perspective, stabilizing the slope, improving vegetation cover, monitoring ground movement, and managing runoff can reduce uncontrolled soil movement, surface erosion, and progressive land degradation. This is consistent with JKR Churun 1, which emphasizes the need for proper maintenance of slopes, maintaining structure, disturbed terrain, and hazard mitigation measures to avoid deterioration and maintaining their function. So secondly, the solution can improve drainage and runoff control. In highland areas, water movement is one of the most important environmental factors affecting slope stability. If surface runoff is not controlled, it can erode exposed soil and overload the drainage system. If infiltration is not controlled, it may increase soil moisture and poor water pressure, which can reduce slope stability. So therefore, the solution should not simply apply to absorb more water, but should manage water safely through proper drainage, control discharge points, and regular maintenance. So thirdly, the proposed solution can reduce erosion and sedimentation. So by protecting exposed slope surface, slowing down runoff, restoring vegetation, and stabilizing loose soil, less eroded material will be transported into drains, rivers, or lower catchment areas. So with this will help reduce drainage blockage, localizing flooding, and water quality deterioration. However, during construction, erosions may temporarily increase due to excavations, stockpile soils, machinery movement, and vegetation clearance. So therefore, temporary erosion control measures such as silt traps, slope covering, stage construction, and regular drain cleaning are important. Lastly, long-term maintenance and monitoring are essential. Drainage system can become blocked, permeable pavement can become clogged, vegetation can fail, sensors can stop working, and slope protection can deteriorate over time. So JKR Churun 1 highlights the importance of routine maintenance inspection, engineering inspection, and monitoring, maintenance manuals, and maintenance record. So the National Slope Master Plan also supports a more systematic approach to slope hazards and risk management in Malaysia. For permeable pavement, public research shows that it can help collect, treat, and filter surface runoff as part of sustainable stormwater management. But however, the Syria Search Manual warns that unlimited permeable pavement should not be used where infiltration may cause slope instability, especially in landslide-prone areas or near embankment and cutting slopes. This shows that permeable pavement must be carefully designed with controlled drainage, especially in highland slope areas. So in conclusion, the proposed sustainable solutions can provide strong environmental benefits, but only if they are properly designed, located, constructed, monitored, and maintained. So the best approach is an integrated system that balances slope safety, water control, ecological recovery, efficient material use, and long-term environmental performance.